On number 9, let S be the portion of the surface x plus y squared is equal to 1 in the first octant that lies below the plane z is equal to 2. So the first thing we're asked to do here is to parameterize it. So R of UV, something, 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 and then we need to give the bounds on u and v here. How are we going to go about doing this? So first thing is that in this formula, there's no z dependence. Z can be anything from 0 to 2, regardless of what x and y are chosen, as long as it's legal here. So let's just make z equal to v, and so one of our bounds is going to be v runs from 0 to 2. The lower bound here on 0 is coming from the fact we're in the first octant. Lying below the plane z is equal to 2 gives us an upper bound here on v. Now, as for the x and the y coordinates, rearranging x plus y squared is equal to 1, solving for x in terms of y gives us x is equal to 1 minus y squared. And so this suggests that we're going to use a parameter u here to replace y, and then in that case, x will just be 1 minus u squared. And from the picture here, in the xy plane, it looks like this. It doesn't take too much to see that the biggest y can be here is 1, and so our bounds on u are going to run from 0 to 1. Okay, so this is our parameterization. For part B, we are asked to evaluate this integral here, the double integral over S, the surface of z ds. So this is a scalar surface integral, and so we don't care about orientation for scalar surface integrals. So the only thing we need to realize here is that in this entire region, z is non-negative, and apart from z is equal to 0, it's going to be strictly positive. And so we're integrating this strictly positive function, other than the part where it's equal to 0 here, we're going to get something positive. So C is the correct answer to part B. Okay, that is problem number 9. Let's take a look at problem number 10 here. So we need to compute the line integral of f dot dr, where f is y plus 2 cosine x, 3x plus 3 to the e to the y squared over this region here. How do we go about doing this? It doesn't tell us to use Green's theorem, but it should be a very good idea for us to be thinking about Green's theorem, because otherwise we have to parameterize and integrate along 1, 2, 3, 4, 5 separate line integrals. I don't really want to do that. But with Green's theorem, we can transform this to a double integral over just one region. So the region here, this will be d right here, double integral over d of partial q partial x minus partial p partial y dA. This is p, this is q. So it's the integral over d. Partial q partial x is 3. Partial p partial y is 1 here. So this is just going to be the double integral over 2 of d. And so this is just 2 times the area of d. And a quick check here says the area of d is 1, 2, 3.5. So 2 times 3.5 is equal to 7. So that's a lot easier than anything else we could have done. Okay, so that's problem number 10. For problem number 11, it'll be again in the same vein here of a Green's theorem kind of problem. So let C, excuse the scribbles right there, let C be the oriented curve shown here, oriented clockwise. We're told that region D bounded by C has area 6. We're asked to evaluate this line integral here. We have no hope of doing this directly because we don't have any parameterization here. So we really are just going to go right ahead to Green's theorem. So where this is P, this is Q. And so what do we have here? Partial Q partial X is 2, partial P partial Y is 0 here. So this is just going to be 2 times the area of D. And so it's 2 times 6 is 12. Now there's one last little catch here. There's one last little catch, which is C is oriented clockwise, not counterclockwise. Green's theorem assumes that our boundary curve is oriented counterclockwise. So how do we account for that? We put a minus sign out in front of all of this. And so our answer here is minus 12. So changing the direction, you know, the line integral along C going counterclockwise would be positive 12. So switching the direction would make this negative 12.